So we're now going to shift our focus just a little bit to talk about another class that we will then come and combine with the executor completion service in order to implement yet another variant of the prime checker app that we've been using as our running example throughout all these different lessons on the executor framework. And this particular discussion is cool because it will give you a chance to learn about a very interesting data structure called a Memoizer. And as you'll see, the Memoizer that we're going to implement will be used to cache the results of long-running function calls and then return cached items, return those cached results if the input is given back to the Memoizer in the future. So it's basically a cache. So memoization is a technique that's commonly used to optimize the performance of concurrent programs, or sequential programs for that matter. We're going to use it for concurrent programs for obvious reasons, as you'll see in a minute. And it speeds things up if you end up with lots of duplicate input and you don't want to recompute long-running calculations to get the results for things that you've already done the computations for. And basically, here's how it works. It caches the results of expensive function calls. And expensive here just means takes a long time to compute. So the way it works is there's a method called computeIfAbsent, which takes a key and a function, where the function is a Java 8 functional interface like function. And if the key doesn't already exist in the cache, then call the long-running function that we just passed in. And when that computation is done, associate the value returned from that long-running function with the key in the cache, and then return the value that's associated with the key. So this is basically a cache, right? You do a computation, you store something in the cache, and then if someone comes along later and asks for the same result, in other words, passes in the same key, then this Memoizer will not have to rerun the long-running expensive function, but instead can just return the cached value that's associated with the key. That's the basic idea. It's a cache. So we're going to come up with a really clever way to do this. This particular approach was described in a nice book by Brian Getz and his colleagues called Java Concurrency in Practice, which came out a long time ago before the advent of Java 8. And they described the Memoizer mechanism. I kind of took it and blinged it out a little bit so it would be useful with Java 8 features, but it's basically the same concepts that are described in Brian's excellent book. And the way we're going to do this is we're going to have the Memoizer cache return a value that's produced by applying a function in the Java 8 sense of a function. So this is the book I was just telling you about, Java Concurrency in Practice. Great book if you want to learn how the classic Java concurrency mechanisms work. If you want to learn the modern Java mechanisms for doing concurrency, this is not the book for you. There's other better books, but if you take my class next fall on parallel functional programming, you'll get a chance to learn all those mechanisms. So the way this works is that there's going to be a value computed for the key, and it'll be returned if it's been computed earlier, rather than having to reapply that long-running expensive function. And what we're going to do here is because we're implementing this as a function, in other words, the Memoizer class is going to implement function, then it's going to inherit its apply interface. And then we can use the Memoizer anywhere where the code expects a function to be used. Where might that be, you could ask? Well, the good example would be for our prime checker app that we've been doing. So here's an example of how this works. If you take a look at the code I'm showing you here, you can see that we're going to define a function that maps a long to a long. So for example, it'll take a prime number candidate, and then it'll return whether or not that prime number candidate's a prime number, or in which case it gets back a 0, or the smallest factor if it's not a prime number. And the way we're going to do this is if we've enabled memoization, then we're going to go ahead and make a Memoizer that will pass in the isPrime method and use that as the function that it computes. And it'll also pass in ConcurrentHashMap in this case, for reasons that'll become more clear in a minute. Conversely, if we're not doing memoization, we'll just pass in the isPrime method reference. So in either case, we either have memoization enabled or memoization disabled. When we call the new prime callable constructor and pass in the random number, we can also pass in the function, which will either be the Memoizer or the non-Memoizer. And that way we can alternate between memoization enabled and memoization disabled. But the code that's actually doing the function doesn't care which of those two approaches we're using. So this is also basically the strategy pattern, if you think about it. Okay, so the way this works under the hood here is we're going to use a concurrent hash map in order to be able to minimize synchronization overhead when used in a multi-threaded program. And the way that this works is it has basically different locking mechanisms available for the different parts of the map. So this has changed over time. In early versions of Java, they had 16 locks that guarded different regions of the hash table. And that was designed to reduce the contention if multiple things hashed at different locations in the hash table that were guarded by different locks, then they wouldn't have to compete with the locks and you'd get better performance. Later versions of the Java concurrent hash map went even further and have basically a compare and swap operation on every single element in the hash table. So it's even more scalable than before. In contrast, a more classic way of doing things, for example, using a synchronized map, would have only one lock. And you can imagine that that would cause a lot of contention because if you had many threads trying to read and write to the, or take input to the hash table at the same time, or I guess it's get input in a hash map model. In that case, you'd end up having all those threads competing for that one and only lock. So it doesn't scale up nearly as well. The way this is going to work is we're going to have the Memoizer's apply method use the computeIfAbsent method on the concurrent hash map to ensure that the function is only run the first time a key is added to the cache. And computeIfAbsent is a very powerful atomic check then act method that's part of concurrent hash map. And here's basically the way it works. So if you take a look at the implementation, you can see that computeIfAbsent takes a key, which is the thing we're going to look up in the map. And then it also takes a mapping function, which could also be written as a method reference too. So this is what computeIfAbsent looks like when it's used with a concurrent hash map. This is the equivalent code that you would have if you were to do this with a single thread. But of course, this is not at all thread safe, but this is sort of kind of the way it works if you think about it logically. So basically what happens is the computeIfAbsent method checks to see if the key is in the map. If it is in the map, it returns the value because it gets back a non-null value. If value is null, that means it's not yet in the map. So in that case, the mapping function is applied to the key and that returns the value. And if the value that comes back is not null, then we put that value into the map with that key. And in any case, we return the value. Now, again, because it's an atomic check then act operation, these steps are actually done atomically and they're done very efficiently. But this is kind of giving you a feel for what it's doing under the hood logically. So one of the cool things about the atomic check then act semantics of computeIfAbsent is only one computation per key is performed. In other words, the function is only called once, even if multiple threads simultaneously call computeIfAbsent using the same key that is not yet in the map. And this is a very important property. We'll talk more about this later when we talk more about future tasks, because I'll show you one way you could implement these semantics using other mechanisms in Java. So that's the end of the overview of how to design a Memoizer for use with the Java Executor Completion Service. As you can see, this is really orthogonal or independent of the Executor Completion Service, but we're going to combine this in just a few lessons with our Prime Checker app and show how all the pieces fit together.